This module is going to be a little bit different. I want to give you guys the opportunity to catch up. I know we've covered a lot of different materials, a lot of different governing equation theories and concepts. So this module and this week, we're going to be reviewing chapters 5 and chapter 6, going through the governing equations again, going through the concepts, and applying it to a couple more example problems. I'm hoping this will help to reiterate some of these theories that we've looked at before we go into our exam number 2. So for this week, we'll review chapter 5 in this module. We'll be taking a look again at the topic of our transient conduction, looking through our lumped capacitance method, our spatial effects and the role of analytical solutions, and our finite difference equations. So as we jump into our chapter 5 review, the first topics we're looking at again are that transient conduction and our lumped capacitance method. This is covering sections 5.1 through 5.3 in your textbook. What is transient conduction? Well, this is going to be a heat transfer process for which the temperature varies with time. So now we can see here, time is going to become a factor as we're looking at this now, as well as with the location as we've seen before when we're dealing with a solid. And this is going to be initiated whenever a system experiences a change in its operating conditions. What are some of these conditions? Well, it can be induced by changes in the following right here. It could be a change in our surface convection conditions, which is our H and our T sub infinity. It could be a change in our surface radiation conditions, our H sub r, our T surround. It could also be a change in our surface temperature or heat flux right there, and or a change in our internal energy generation. So all of these right here could be the changes that we're referring to. So we have a couple different options when we're going for our solutions right here, and we've seen this throughout this semester, throughout all these different modules here, that there's always a different way. There's multiple ways to solve these problems right here, and we're just showing you more and more options for you to choose from as you're going through. So the same holds true for this here. So some of our solution techniques include this new lumped capacitance method. We could go for exact solutions, or we could go back and take a look at our finite difference method again. So as we continue on now, let's take a look at our lumped capacitance method right here. So for this method, we're going to be making a big assumption right here. It's going to be based on the assumption of a spatially uniform temperature distribution throughout the entire transient process right here. So if we're talking about a spatially uniform temperature distribution, we can look at this equation right here, that our T with respect here to our R comma T right there is going to be approximately equal to T just relative to our time right there. So T of T right there, where lowercase t is our time right there. So this is an assumption that we can make, an approximation that we can make based upon the assumption of a spatially uniform temperature distribution. So now if we continue on with our general lumped capacitance analysis right here, we want to consider a general case. For this general case, what we're going to consider here is it's going to include convection, radiation, and or an applied heat flux at a specified surface. So surfaces we're going to look at here are our A, S, comma C right there, our ASR, which is also here on the same surface over here like that, and our ASH right there. We can see at our surface ASH right there, we have this imposed heat flux right there, our Q sub S double prime. Now if we look over here at our A sub SC or A sub SR right there for that surface over there, now we can see a radiation and a convection term over here that we'll have to deal with. Now we can also see here is our surroundings over here. Here's the temperature of our surroundings there. And for our material right here, we can see we have a rho, C, V, and an initial temperature T of 0 is equal to T sub I right there. And we have our E sub G dot and our stored energy term right there, E sub ST dot right there. So a thing we want to note about this particular example that we're talking about here is that this imposed heat flux right here, our Q sub S double prime, and the convection radiation heat transfer over here, so our imposed heat flux and our convection and radiation heat transfer terms over there are going to occur mutually exclusive portions of the surfaces right there, our A sub S comma H and our A sub S comma CR right there. So that is going to be respectively right there with our heat flux occurring at this surface right here and our convection radiation occurring at this surface right here. Now our convection radiation transfer is going to be presumed to be from that surface right there. So you can see these arrows coming out right there. There's our radiation term, there's our convection term coming from that surface right there. Now, even though we can look at this and we can see that our convection and radiation have been prescribed from the same surface right there, for our convection term and our radiation term come from that same surface right there, the surfaces, in fact, may differ. So we can see here that this is not necessarily true that these are going to be equal. So these might not be equal to each other right there. So our A sub SC could very much not be equal to our A sub SR, and it's probably not going to be equal to it. So now as we continue on with our lump capacitance method here, we want to go back and review our first law right here now. So we can come over here and we have this general equation right here. We have our partial with respect to time of our EST, where EST is going to be the rate of increase of energy stored within a control volume, having units of watts right there. And this is equal to our rho value right there, which is our mass density, units of kilograms per meters cubed right there, times now our volume right here in meters cubed right there, times C, which is our specific heat in units of joules per kilograms times Kelvin right there. And this is times our partial of temperature with respect to time. Now this is going to be equal to, right here, our E dot in right there, which is going to be the rate of energy transfer into the control volume in units of watts again right there, minus our E dot out right there, which is going to be our rate of energy out of the control volume, still in units of watts right there, plus our E dot sub G right here, which is going to be the rate of energy generation, again, in units of watts right there. Now, one thing I would highly encourage you to do with any of these problems right there, especially as we're coming into these equations, we're plugging one equation into another equation right there, is double check your units. Do out your unit analysis, make sure things cancel out, and end up with the correct units in the end that you would expect them to have. Now, if we're going to assume an outflow due to convection and radiation, and an inflow due to an applied heat flux right here, then we have the following relationship, which goes back to equation 5.15 in our textbook right here, which we have again our rho VC, which again our rho, we can go up top here, is our mass density in kilograms per meter cubed. We have our V right here, which again is our volume in meters cubed right there. And we have our C value right there, which is our specific heat in joules per kilogram times Kelvin right there. And this is times our dt, which is our change in temperature with respect to time right there. Now this is equal to, now down here, our heat flux right there, times A sub S comma H, which is the surface area due to conduction right there, minus our A sub S comma C right there, which is our surface area due to convection right there, times our temperature difference of T minus T infinity, where T infinity is our surrounding fluid temperature right there, minus our H sub R, which our H sub R right here is going to be the convection due to our radiation right there, and this is times our A sub SR right there, which is our surface area due to radiation as well right there, times our temperature difference between our temperature and our surface temperature right there, plus our E dot sub G right there, which again is our rate of energy generation in watts right there. And this is going to relate back to our equation 5.15 in our textbook. So now what I've done on this page right here is something that I highly suggest you do as you're working through your problems, whether it's all on the same page as you're doing out your problems, or if you have this on your setup page, or maybe you have a governing equations page. That's actually what the ideal situation right there is. If you have a governing equations page, you can write out what your governing equations are. You can even write from the back of the textbook or the name of the equation right there, but then have all of the terms within these equations listed out with how they relate to your problem, what the variable name is, and what the units are right there as well. So all of that's going to make your life really easy, and you could even include within this, if any of this was given to you, you could say equal to whatever the value is that is given to you. So you could have all four of those things that we talked about before: the variable name, the numerical value, the units you're using, and how it relates to your problem, all on the same type of page here. Again, if you don't have the numerical values for all of them, still including three of the four things is still great. The variable name, the units you're using, and how it relates to your governing equation right there is very, very useful. It's going to make your life a lot easier as you start plugging in to these different governing equations for your solution to the problem. So now as we continue on with our review of Chapter 5, we're going to go back through and look at sections 5.4 through 5.8 in our textbook. This is looking at the areas of transient conduction, specifically our spatial effects and the role of analytical solutions. So as we continue our review of this section of our Chapter 5, I want to consider a few things. What about the situation that frequently arises where our Biot number is not small? So when this occurs, we need to cope with the fact that our temperature gradients within the medium are no longer negligible. So we can't neglect these temperature gradients anymore, which makes the problem slightly more complicated. Also, the use of our lump capacitance method would yield incorrect results for this. So there are alternative approaches that are presented within this section of Chapter 5 that we can utilize. So continuing on with this, let's take a look at a simple situation here where we have a plane wall with symmetrical convection conditions right here. So if we want to find the solution to the heat equation for this plane wall right here, what we would realize is for a small Biot number, the lump capacitance method no longer is possible. So if this lump capacitance approximation cannot be made because it has a larger Biot number right now, then a consideration must be given to our spatial as well as our temporal variations in temperature during the transient process. So now let's take a look over here at our plane wall in this figure right here, and we can see, okay, there's our center line right here. We can see we go out an equal distance to L right here in our x direction here, and a distance of L right here in our negative x direction there. We can see we have a initial condition right here, that we have our T at a position right here of x right here is equal to T sub I, our initial temperature right there, and we can see we have our surrounding T infinity and H values symmetric on either side of this wall right here. So this is for a plane wall with symmetrical convection conditions and constant properties that we've just shown in our diagram off here to the right. So the heat equation and initial boundary conditions are given as the following, and this relates back to equations 5.29 to 5.33 in your textbook right there, where 5.29 gives us our initial temperature distribution plane with no internal generation and the assumption of constant thermal conductivity right there. So that comes down to this 5.29 there. We have our delta squared T over dx squared right there. So we're allowed up to x right there. This is equal to 1 over our alpha times our dt right there, our delta of temperature right there with respect to time there. So that's our equation 5.29. So then we can take a look at our initial condition here in equation 5.30. So this initial condition presumes a uniform temperature at time t is equal to 0. So you can see right there, there's our t is equal to 0 for any x right there. So temperature for any x at time is equal to 0 is equal to our initial temperature right there, T sub I. So this is a uniform temperature distribution regardless of where it is, where the location in x direction at initial time of T is equal to 0. Then we can go on to our boundary conditions, and in equation 5.31 we look at the boundary condition here that reflects the symmetry requirement for the midplane of the wall right there. So again, we saw that there was symmetry about that right there. So with this here, we have our partial of T with respect to x, partial of temperature with respect to our position in the x direction going out like this here. When x is equal to 0, and we're right at that midline right there, then our partial of temperature with respect to x is also equal to 0. So again, that goes back to a relationship shown here in equation 5.31. And our next boundary condition here, equation 5.32, this describes a surface condition experienced for a time greater than 0 right there. So when it's not a time of 0, when it's greater than 0 right there, we can say our negative K, our thermal conductivity right here, times our partial of temperature with respect to position, delta T, delta X right there, evaluated at some X is equal to L. So L is out here at the end right here at the outside walls of this right there. And this is equal to H. There's our H value right there, the same on both sides right there for convection right there, times now our temperature difference between now our temperature of L comma T. So when X is equal to L and our time is equal to some T right there, which is a time greater than 0 right there, minus temperature of our surrounding, T infinity right there, and this is now our equation 5.32. So with this here, we can go on to equation 5.33, and this shows the existence of 8 independent variables right here. So we can take a look. T is equal to T of our x, position x right there. So coming off of this is our x right there. Our time, initial temperature, temperature of the surrounding, our value of L right there out the outside surface, our thermal conductivity, our alpha term, and our H term as well. So all these are 8 independent variables that are shown right here that our temperature is dependent upon right there in equation 5.33 in our textbook. So now I want to talk about the non-dimensionalization of the heat equation and initial boundary conditions. We're going to do this still for that plane wall example we saw on the previous slide right there. So within this here, let's first take a look at our dimensionless temperature difference right here. So we have our theta star right there. So our star right here is going to denote this is dealing with dimensionless right there. So this is equal to our theta over theta I right there, our temperature difference over our initial temperature difference right there, which relates to equation 5.34 in our textbook right there, where we have our T, our temperature of interest right there, minus our T surrounding right there, T infinity, all over our initial temperature minus the temperature of the surrounding right there. So that'll give us our dimensionless temperature difference right there. So next, let's take a look at our dimensionless space coordinates. So recall here, if we're dealing with space here, we're dealing with our x direction here for this 1D plane wall. So this is going to be our x star right there, which relates back to our equation 5.35 in our textbook right here, where we have our x over L, where our L in this case here, if we remember back to that diagram of our plane wall right there, L is going to be half the thickness of the plane wall because it's going to be symmetric about that midline right there. So from there, if we're talking about our dimensionless space, let's also talk about our dimensionless time right here, or our T star right there. Now this is going to be equal to our alpha over L squared right there, which is equal to our Fourier number. So we call here our F sub 0 or F sub O right there is our Fourier number there. So that's saying our dimensionless time is our Fourier number, and this is our giving relationship right there, this alpha T over L squared right there. And this relates back to equation 5.36 in our textbook. Now from here we can go on to our Biot number that's dimensionless as well. Recall that this relationship here is our Biot number is equal to our H times our L right there, all over our thermal conductivity K value for the solid right there. So this, recall, is our Biot number that we've seen previously. So with all this here, now what we can say is that this theta star right there, our dimensionless temperature difference right there, is going to be a function of our x star, which is our dimensionless space coordinate, our Fourier's number, which is also, as we just saw up here, our dimensionless time unit right there, and our Biot number. So all of these are dimensionless right there. Our x star, our Fourier number, and our Biot number right there. So this is what our theta star right there, our dimensionless temperature difference, is a function of all three of those. So now if we want to take a look at our exact solution, we have some equations that we can reference back in our textbook. Particularly, let's take a look at this equation 5.42a, where here now we have a relationship for our plane wall right here for our theta star right there, which again is our dimensionless temperature difference right here. And this is equal to the summation from n is equal to 1 to infinity right here of our Cn times the exponent here of a negative eigenvalue squared times our Fourier number right here times the cosine of our eigenvalue times our x star right there, where again we come back up here on our x star is this dimensionless space coordinate right here, where again this is still dealing with our plane wall right here, and L is the half thickness of that plane wall right there as we plug in for that x star right there for our dimensionless space coordinate. So that makes up our equation 5.42a. Now the question is, well, what is this C sub n right here? Well, we have this relationship here that our C sub n is equal to 4 times the sine of our eigenvalue, all divided by 2 times the eigenvalue plus sine of 2 times our eigenvalue right there. And we also have the relationship now in equation 5.42 here for our Biot number. So our C sub n and our Biot number, we can reference back to 5.42 B and C in our textbook right there, where our Biot number is now our eigenvalue times the tangent of our eigenvalue there. Where now the question is, well, what are these eigenvalues right here? So we can go to our appendix B3 in our textbook, and we can look at the first 4 roots for our eigenvalues for 1, 2, 3, and 4 right there, and plug it back in to this equation. So now let's actually go to the appendix in the back of our book, take a look, and find our appendix B3. So again, in B3, this gives us the first 4 roots of our transcendental equation right there. So we can look up our values, our eigenvalues right there, and recall right there we have that relationship we just saw in our previous slide. It even gives it to us in that appendix right there, that our eigenvalue times the tangent of our eigenvalue is equal to our Biot number. And this is for the transient conduction in a plane wall. So again, we're just looking at transient conduction for that plane wall example from before. We also see now there's our relationship for our Biot number right here, where Biot number is equal to H times L over K right there. So now we can look here for our eigenvalues again, the first 4 roots, 1, 2, 3, and 4, are all given in this table right here for these Biot numbers right there. So next I want to take a look at some approximate solutions. In particular, let's take a look at our one-term approximation. What we want to note about this one-term approximation here is this is only going to be valid for Fourier's number greater than 0.2. So in order to use this approximation right here, we need to make sure that this is valid right here and that Fourier's is greater than 0.2. We see that the variation of our midplane temperature right here, and again, we go over here, what is our midplane right there? This is our midplane right there. So this is when x star is equal to 0 right there, going right up that there. So you can see that's our x value going over here. So when this is equal to 0, we're at that midplane right there. And with a time of our dimensionless time, our Fourier number right there. Again, we go back to our previous slide, and we can see that this Fourier number is our dimensionless time. So for that, then we can say that this equation 5.44 holds true right here, where we can say our dimensionless temperature difference, our theta at that midplane right there, star is equal to our temperature at the midplane minus our surrounding temperature right there, all divided by our initial temperature minus our surrounding temperature there, which is equal to our C1 times the exponent of our eigenvalue squared times our Fourier number right there. So again, this references back to equation 5.44 in our textbook. Now for our values, our coefficients right here, our C1 and our eigenvalue 1 term right here, we can go to our table 5.1 in our textbook, and we can get these, and we can see that these 2 coefficients are a function of our Biot number. Now we can also evaluate these coefficients with equations 5.42b and 5.42c in our textbook. So looking at the variation of temperature with our location, our dimensionless location right here, our x star, and time right here, Fourier's number, our dimensionless time right there, we can go now to reference equation 5.43b in our textbook that tells us that our theta star right here, our dimensionless temperature difference, is equal to our theta 0 star, which is our at the midplane right there, which we have this equation up here from 5.44 for that right there, times the cosine now of our eigenvalue times our x star right there, which is our dimensionless space coordinate right there. So this references back to equation 5.43b in our textbook. Now moving on from there, if we want to take a look at our change in thermal energy storage with time, we have these equations here, 5.46a, 5.49, and 5.47 in our textbook right here, where 5.46a shows us this delta E right here, our change in our thermal energy storage is equal to our negative Q. Well, the question is, well, what is Q? That's where we can go to equation 5.49 in our textbook and see that Q is equal to our Q not right there, Q at 0 right there at our midplane right there, times 1 minus the sign of our eigenvalue 1 all over our eigenvalue 1 there, times now this relationship right here for our dimensionless temperature difference, which we see we have this equation for up here in 5.44. And then we can say, well, what is our Q at 0 right there? Well, Q at 0 is 0, which is our midplane right there, is equal to rho VC times our temperature difference, our initial temperature minus our surrounding temperature right there. So we need to plug all these in. We can plug this relationship in for our Q naught right there, and then we can multiply that by this relationship right here, and that whole term right here comes up here with a negative sign in front of it right there, and that gives us our change in our thermal energy storage with time. Now let's go back and take a look at our textbook here at that table that we referenced there, our table 5.1, where this gives us the coefficients used in one-term approximations. So again, this is just for the one-term approximation to the series solutions for transient one-dimensional conduction. So very specific right there. Make sure when you're using these tables, you do look at them and see what they apply to. So that's the case here. We can see now we have our Biot number right here, and we can see our eigenvalue and our coefficients right here for a plane wall, an infinite cylinder, and a sphere. So we have for all three of those simple geometric shapes. Well, as we look at our last section as we review our chapter 5, this is our section 5.10, which relates to, again, transient conduction, but now looking at our finite difference equations. So let's get into the topic of this finite difference method. So what is the finite difference method? We've looked at this a little bit before. So just a refresher, this finite difference method is an approximate method. So again, this is an approximate method. That's something that's important to note there. And this is for determining temperatures at discrete nodal points of the physical system and at discrete times during the transient process. So within this, what we want to do is establish a procedure for how we can go about in a methodic way for solving these type of problems using this finite difference method. So for our procedure, what we want to do is we want to represent the physical system by a nodal network. Now within this nodal network, we want to utilize this MN notation to designate the location of these discrete points within the network. And then we want to discretize the problem in time. So we're doing this as time as well by designating a time increment now, our delta t, and expressing the time as the relationship that we see here, that time is equal to p delta t, where p assumes integral values right here from p is equal to 0, 1, 2, and keeps going on. So going back to our mn, so again, the way to think of this MN notation right here is the same way as like a Cartesian coordinate system. We're using our x, y, and that designates the location of where these things are from an origin point. So this is similar to what we did earlier in this module as well, utilizing that same MN notation. So now once we've represented this physical system by a nodal network, the next thing we want to do is go back to our energy balance method and use that to obtain finite difference equation for each node of an unknown temperature. So we're looking at each node within that nodal network and using the energy balance method to obtain that finite difference equation. So once we have those equations, the next step would be to actually go through and solve those equations. So solving the resulting set of equations for the nodal temperatures at, again, our time right here, time is equal to delta T, 2 times delta T, 3 times delta T, and so on. So now one thing we want to ask ourselves here is what is represented by this value right here for this variable here? We see T to the P subscript M comma N. Well, let's break this down a little bit. The superscript P that we see right up top here is used to denote the time dependence of our temperature. And the time derivative expressed in terms of the difference in temperatures as associated with the new P plus 1 and the previous P times right there. So that's how we're denoting between those. So hence the calculations must be performed at successive times separated by the interval of our delta T. And just as a finite difference solution restricts temperature determination to discrete points in space, it also restricts to discrete points in time as well. So as we were looking through that procedure that we wrote up on the previous slide, one thing that we noticed is that there was an energy balance equation we need to deal with there. So now for our energy storage term, let's take a look at this energy balance and our finite difference approximation for the storage term right there. So if we think about our energy balance right here, for any nodal region, the energy balance is going to be given by this relationship shown in our equation 5.84, where we have our E dot in plus our E dot G is equal to our EST, where E dot in is our rate of energy transferred into a control volume in units of watts. Our E dot G is the rate of energy generation in watts, and our EST is the rate of increase of energy stored within the control volume in units of watts as well. Now, according to convection, all heat flow is going to be assumed to be in the region. So looking at the discretization of temperature variation with time, we have this equation 5.77. So this equation here shows us that our partial of temperature with respect to time evaluated at some mn is approximately equal to, now there's that variable we saw before for temperature right there, our temperature mn at P plus 1 minus our temperature Mn at P right there. So then this is with time right there, and we recall that superscript had to deal with time points right there. And this is all divided by our delta T value right there. So now let's take a look at our finite difference form of this storage term right there. So this says now right here that our E dot ST of Mn right there at that position right there is equal to our rho Vc, our density, our volume, and our specific heat, times now we have this fraction over here. We're on the numerator. Again, we have that same term we have up here, that temperature superscript P plus 1 of Mn minus the temperature at P of Mn right there, all divided by that delta T right there, which is exactly from this equation up here, 5.77. Now we have the existence of two options for the time at which all other terms in the energy balance are evaluated here. This is either a P or a P plus 1. Now just let's note here, the P is used to denote the time dependence of that temperature, and the time derivation is expressed in terms of the difference in temperatures associated with the new P plus 1 and the previous P times. So now that we've gone through an overview of Chapter 5, refreshing our memories on those topics, key equations, and governing theories, what we want to do now is apply all of those to an example problem. So now we're going to take a look at this example problem, 5.17. I'll go through my hand solution and relate back to some of the governing equations and theories that we utilize within Chapter 5. Let's first take a look at problem 5.17. In this problem, we have a small spherical particles with diameter d is equal to 50 micrometers that contain a fluorescent material that, when irradiated with white light, emits at a wavelength corresponding to the material's temperature. Hence, the color of the particle varies with the temperature. Because the small particles are neutrally buoyant in liquid water, a researcher wishes to use them to measure instantaneous local water temperatures in a turbulent flow by observing their emitted colors. If the particles are characterized by a density, specific heat, and thermal conductivity that are given here, where density equals 999 kilograms per meter cubed, K is equal to 1.2 watts per meter times Kelvin, and our specific heat is equal to 1200 joules per kilogram times Kelvin, respectively, they want us to then determine the time constants of the particle. One hint here is that since the particles travel with the flow, heat transfer between the particle and the fluid occurs by conduction. Assume lumped capacitance behavior. So that gives us a few hints on how we're going to set up this problem and what assumptions we're going to make. So now let's take that information from our given problem statement and organize it into a format that we're used to make it a little bit easier for us to visualize what's going on, all the variables that are given to us, what they're asking us to solve for, and what assumptions we should make. So we go to the information from problem statement 5.17. We know we have these spherical particles over here. We know that there's a diameter, capital D, of 50 micrometers. We have a density of 999 kilograms per meter cubed. We have a K value of 1.2 watts per meters times Kelvin. We have a specific heat of 1200 joules per kilogram times Kelvin. We know that surrounding temperature here, water here, in this case is 300 Kelvin. Now, in this problem, they want us to find the time constant of the particles. We call this tau sub t for our variable name. And we're going to make three different assumptions within this problem. We're going to, 1, assume constant properties. 2, assume an infinite medium. And 3, we're going to assume lumped capacitance behavior. Now that we have all the given information laid out in front of us in easy to read format, the next step is to start thinking about our solution. So we look at everything that's given to us, what they're asking us to solve for, and what assumptions we're making. From there, choose some generalized equations in order to start the solution to this problem. So the first thing we want to take a look at for this particular problem is the fact that we're going to need our shape factor. So for our shape factor, we can go to table 4.1 on page 236 and take a look at case 1. So now we'll take a break and switch over to the book and take a look at table 4.1. So now we can see table 4.1 from page 236 of our textbook. This is for conduction shape factors and dimensionless conduction heat rates for selected systems. Now for our particular one, we're just going to look at case 1 here. So isothermal sphere, so we're dealing with spheres here, buried in a semi-infinite medium. So this relates to our case here. And we're going to assume that we have z approaching infinity here. So we're going to use this relationship over here for our shape factor based off of case 1 from table 4.1. We have 2 pi d over 1 minus d over 4z. Now we can relate back over here. You can see 2T is our surface temperature, T1 is the temperature of our sphere, D is the diameter of our sphere, and Z is going to be the depth. So now that we've gone to table 4.1 and taken a look at case 1, which relates to our particular application for the sphere and our problem here, we saw this diagram here that I've redrawn. And we know that for our case, z is going to approach infinity. So again, there's our temperature of the sphere, diameter, our depth here. This was our shape factor equation that we were taking right from table 4.1 for our case, 2 pi d over 1 minus d over 4z. And for our case here, again, we're going to let z approach infinity. So as z approaches infinity, this relationship over here, we're divided by infinity here, this whole fraction becomes 0, so we're left with 2 pi d over 1 minus 0, or our shape factor is equal to 2 pi d for the specific case where z approaches infinity. So now that we have a simplified version of our shape factor equation with z approaching infinity here, what we want to do is go back to the top of table 4.1 and take a look at our general equation for shape factor here, where q is equal to s K times the temperature difference between T1 and T2. So now we'll take that equation and plug back in. So from this newfound relationship for our H value here, we do see that we have this S, or our shape factor, that needs to go into the numerator of this relationship. Now recall, we've just solved for this from our table 4.1 in our text, and we reduced this down, simplified it for our specific case where z approaches infinity. We got the fact that for our sphere here, the shape factor is equal to 2 pi d. So we can take this relationship from our shape factor here, plug it back into our equation that we've now solved for h, and we end up with this relationship here, that h is equal to 2 pi d, so that replaces our shape factor s with this value here, times our k value divided by pi d squared. Now we can see here that a lot of things will cancel out. Our pi cancels with our pi, our d in the top numerator cancels with our d squared. In the denominator here, we can reduce and simplify, and we end up with an expression now for h with the shape factor plugged in, that h is equal to 2k over d. So recall that what we're really looking for here is our thermal time constant. So tau sub t is what we're looking for, so we can go back to equation 5.7 on page 282 of our textbook, and we can come up with this relationship here for our general equation. So our time constant here, our thermal time constant, tau sub t, is equal to 1 over our h times as times rho v c. So our h is what we just solved for up here, the previous part of the solution here of 2kd. So we can plug this in to equation 5.7 for our value for h here. And when we do that, we end up with tau sub t is equal to 1 over, now here's our h value here, 2k over d times a sub s times rho v cp. We can rearrange this slightly, and we can find that tau sub t is equal to now d, when we move this around, put this back up from the denominator up to the numerator, d divided by 2k as times rho v c sub p. So this is now our generalized expression for our particular case here for tau sub t, or our thermal time constant. So we can then take this relationship for tau sub t that we just solved for here and simplify it down one step further. Take everything on the right, our rho v c sub p, put it over on the numerator here, and we end up that tau sub t is equal to d rho v cp all over 2k times a sub s. So now let's start plugging in for what we know in this problem here. So remember, we're dealing with a sphere. So for a sphere, we have values for area and volume for equations that we can plug in. So our a sub s for this guy here is equal to pi r, 4 pi r squared. But if we don't want to deal with radius, we want to deal with diameter, we can say, okay, pi d squared. Then if we have volume, we have 4/3 pi r cubed. We can again change it from radius to diameter. We end up with 4/3 pi times d over 2 cubed, or pi d cubed over 6. So now we have a value for a sub s, and we have a value for v. So we can plug both of those into this equation here. We end up with tau sub t is equal to our diameter d times rho. Now our volume from this guy here is pi d cubed over 6 times c sub p. On the bottom we have 2k, where we had a sub s. We now have our a sub s was pi d squared. So here is our pi d squared to replace our a sub s here. And we end up with this relationship here for tau sub t. Well, now we can again see there's a lot of things that are going to cancel here. So we have our d cancel with our d, our pi with our pi, squared, cubed there. We're just left with a d on top over here now. So now as we go through this here, we can simplify it down one step further, and we end up with, in the relationship here, tau sub t is equal to rho d squared cp over 12k, once we've reduced and simplified everything down. So now that we've simplified down our expression for tau sub t, we can now see that we have a lot of variables here that we already have values for that we can plug in. So we have our density, specific heat, diameter, 12, and a k value. But now what we want to be careful of here is the k value they gave us for, in the problem statement was for the particle here. We really need to look at this for our specific case here for tau sub t for our saturated water. So if we want our thermal properties for saturated water, we need to go to table A6 in our appendices here in order to get this value for K here. So we'll take a break, switch over, and take a look at table A6. So now we go to table A6, thermophysical properties of saturated water. We know that our temperature is given to us as 300 K here, so I've boxed this in here. You can see they give us pressure, specific volume, vaporization, specific heat, viscosity, and thermal conductivity. So this is what we're interested here, is thermal conductivity, our K sub F value. So we go down here, this is 613, but pay attention, this is times 10 to the third. So for our specific case here, we're going to have A sub 6, temperature is equal to 300 K of 0.0613 watts per meter times Kelvin. So again, we had to pay attention to our units here because there's a 10 to the third. So now we have our K value here for saturated water of 0.613. So we can go back to our tau sub T equation and plug in all of these values here. So now that we have our correct value for K from table 8.6, we can go back to our simplified expression for tau sub T, rho, specific heat, diameter, and our K value here. Plug in what we know. A rho, 999 kilograms per meter cubed, we can plug in here. C sub P, specific heat, 1200 joules per kilogram times Kelvin, we can plug in here. Diameter D of 50 times 10 to the negative 6 when we're dealing with meters, plug in there. And now our K value we have down here from table A6, we can plug in 0.613 watts per meters times Kelvin. Plug all these values into this equation, we end up with this expression here. Tau sub T is equal to 999 kilograms per meter cubed.
times 1200 joules per kilogram times Kelvin times 50 times 10 to the negative 6 meters quantity squared. And on the bottom, we have 12 times 0.613 watts per meters times Kelvin. Go through, cancel out, do some unit analysis. We end up, once we simplify the numerator, to 0.002997 in units when we reduce down of joules, meters times Kelvin here. And then on the bottom, our denominator, we multiply these out, 7.36 watts per meters times Kelvin. Cancel out our units here. What we're left with, in this case here, is tau sub t is equal to 407 times 10 to the negative 6 in seconds in the correct units that we want. So this is our value. This is what they asked us to solve for in the problem.
Separately, I just wanted to include this table A6 again that you saw in my video solution, so that you'll have it here as well as in the video portion of my hand solution, and this will also be saved as a PDF for you to reference as well within this review of Chapter 5 in this module. I also wanted to include table 4.1 as well here separately from my hand solution, so you can reference back to this both in this video as well as the PDF posted on Blackboard for this review of Chapter 5 module. Now for this review of our Chapter 5, I've also included my hand solution to several more problems. This is one of the problems that I'll go through my hand solution for as well, this example 5.5. So please go to Blackboard and reference this PDF that I've posted with all my hand solutions for these different example problems. As you're going through and looking at my hand solutions to this example problem, I've also put this up here, table A1, so you can see where I'm getting this information from, and you can follow along and solve these problems with me. Another table that we're going to utilize within this solution is our table 5.1. So again, as you're going through my hand solutions, following along and solving them yourself, you can reference back to this table as well. The next problem I'll go through my hand solutions is problem 5.15. So again, I posted this up here as well, so you can follow along and solve this with me. Along with this, as you're going through the solution to this problem, you can see you'll need to utilize this table A1. So again, I've posted this here within the video. It will also be posted as the PDF on Blackboard as well. So as you're going through my hand solutions, you can follow along and see where I get these values from. And the last table you're going to utilize within the solution to this example problem is this table 5.1. So again, please reference this, and you can see where I've boxed in where I've gotten my values as I've gone through my hand solution.